Hello everyone. So in this lesson we're going to continue with the overall topic of parametric equations, and specifically we're going to continue talking about a topic from the previous lesson. That is, we're going to do more with modeling motion. And as part of that, we're going to talk about something called projectile motion. And the reason we're revisiting this topic again is last lesson was a little intro to this topic, but we kept it a little too simple. So let's see how we can dive deeper into this topic. So here's the kind of example that we saw in the last lesson. It says, suppose a remote-controlled car is traveling through a parking lot at constant speed. Let its starting position be 7,4 in meters away from the boy controlling it. Its horizontal speed is 20 meters per second going right, and its vertical speed is 11.5 meters per second going up or forward. Model the car's movement with a set of parametric equations. So first of all, notice that in this situation, we're kind of dealing with a top-down situation where we're looking down at the car. So let's say, here's the car. And it's at position 7,4. You know, like maybe the boy is here. And it's 7 meters to the right and 4 meters up or forward. And notice that the movement is broken down into horizontal speed and vertical speed. So horizontal speed, 20 meters per second going right. So this car, as it moves, its x position is increasing at a constant rate going this way by 20 meters per second. And then its vertical speed, 11.5 meters per second. So its y position is increasing by 11.5 meters per second. So it's going like this, right? And the way they've given us this information, it's pretty easy to come up with parametric equations for the motion. So we've got the x value of the car starts at 7 plus, it's a constant rate, so 20 plus 20 per second, so plus 20t. And then its y value starts at 4. And then we're going up or forward, so plus 11.5 per second, and we're done. These equations give the position of the car after t seconds have passed. But the issue with this problem is, if you think about it, it's not very realistic to be given the horizontal and vertical speed of something. It's not very realistic to have those speeds broken down. Because what's really going on here is, if it's going right at this speed and up at that speed, really what we would be seeing in real life is it would be going diagonally, right? Bit to the right, bit forward, it would be moving this direction and the car should be facing that direction. So let's look at a problem that's more realistic or makes more sense than being given the horizontal and vertical speeds separately. So here's a very similar example, but it's a little more realistic. It says, suppose a remote-controlled car is traveling through a parking lot at a constant speed of 15 meters per second and at a direction of 280 degrees in the usual sense that we work with angles, right? Counterclockwise relative from 0 degrees in the positive x direction. Let its starting position be 7,4 in meters away from the boy controlling it. Model the car's movement with a set of parametric equations. So how is this problem a little more realistic than the previous one? Well, it just gives us a single speed, 15 meters per second. And if you think about it, that's more realistic in the sense that when we talk about speeds in the real world, we don't break it down into different components, right? We don't break the speed down into a horizontal speed and a vertical speed. We just talk about, oh, that car is going at however many miles per hour, or that airplane's going at however many. So in that sense, this single speed of the car makes more sense. But to do any math with it, we do need a direction. So it gives us a direction of 280 degrees. And so this makes more sense, but now it's unclear how we're going to write the equations. So let's sketch the situation. So let's say here's the car. That's actually probably not the way it's facing. And then 15 meters per second at a direction of 280 degrees. So how we do the math here then is You need to look at this info, 15 meters per second, direction 280 degrees, and recognize that what we're really dealing with here is a vector. So in a previous lesson, we learned about velocity vectors, and this 15 meters per second, that would be the magnitude of the velocity vector, and the direction 280, well, that's just the direction of the vector. So where is 280? 0 degrees is this way, as usual. And then 280, we go 90, 180, 270, so a little bit past 270 going this way. So our car really should be facing this way. Its starting position, like in the previous example, is 7, 4. So there's our sketch. And the question is, how are we going to break this down into an x and a y equation so that we know its position over time? Because yes, the situation is more realistic, but now we actually need the horizontal and vertical speeds to write the equation, right? But now, assuming that you've seen our previous lessons with vectors, we actually already have the math to break this velocity down into its horizontal and vertical components. We can figure out what combination of horizontal speed going this way and what vertical speed going that way is the same as going 15 meters per second at a direction of 280 degrees. So how do we know? Well, remember this formula here, and remember what this formula is. This formula is how you take a vector, given the magnitude and the direction, and break it down into component form, right? As in, this is the horizontal component of the vector, and this is the vertical component of the vector. So in our sketch, we have, okay, the magnitude is 15 meters per second. But using this formula, the horizontal and vertical components, right, the speed here and the speed there, those are 15 cosine 280, comma 15 sine 280. Remember, this formula is super straightforward if you have the magnitude and direction. And we get around 2.6047 for the horizontal component. Remember, that's in meters per second. And then negative 14.7721 around for the vertical component. And note that it makes sense that the vertical component is negative because we're going down, right? Down as in this direction. So now we have taken the vector they've given us, essentially, and we figured out, okay, this velocity can be broken into 2.6047 meters per second going that way, and negative 14.7721 meters per second going this way. And now the equation's easy in the sense that it's the same as what we did in the previous problem. So for example, x equals, how do we get the x position over time? Starts at 7, and it moves at a constant speed of around 2.6047 per second. So it increases by that amount per second times t. What about y? So we start at 4, and then every second we subtract this same amount, 14.7721, around that per second times t. So there's our equations for giving the position of the car over time. Like in the previous lesson, note that both in the horizontal and vertical directions, this is a constant rate of change sort of situation. So we've got two linear equations. And so once we've gotten these equations down, then we can use them to calculate things about the car's position over time, right? Like, where is the car's position at this many seconds? Or how many seconds does it take for the car to get to this position? Stuff like that. So now let's talk about something called projectile motion. And projectile motion just means the motion of objects moving or falling through the air, and specifically with the only significant force acting on it being the force of gravity. And you know, this projectile motion, it's a pretty important type of motion. It's pretty relevant to the physical world we live in, right? And if you recall, we kind of did problems with this projectile motion in the previous lesson, except we kept it too simple. Because the projectile motion we talked about in the previous lesson, we kept it to objects that fall on their own without being launched. So what do I mean? In those problems, we had an object, and then it just started falling at time equals 0 seconds, like this. And then I told you a simple formula that models the height over time. Y equals the starting height minus half the acceleration of gravity times the time squared. But again, that formula is too simple because we haven't taken into account the possibility of launching the object. So let's say you have an object that's going to be moving, and let's say you're launching it, throwing it, shooting it upwards and diagonally like this. Now, rather than falling like this, instead it's going to start going like this and then fall later and make a parabola like that, right? And in this situation, the formula for the height becomes more complicated. So here's the full formula, which you may learn or may have learned in a physics course or maybe an Algebra 2 course. And you know, this formula is kind of similar to the one I already gave you, except there's new stuff in the middle. So what is going on here? First of all, we got y equals and then y sub 0. So this just means the initial height, as in what is the y position when the object starts moving? Initial height. And then let's explain what we know already. This part is the contribution from gravity. And then the a sub g is the acceleration due to gravity. You know, so that a sub g is like 9.8 when you're dealing with meters and seconds, or around 32 when you're dealing with feet and seconds. But then what about this middle part? So we have this v sub y 0, and then times t. T is just time, of course. But this v sub y 0, that's the initial vertical velocity. So initial vertical velocity or initial y velocity. So what's going on? This object is being launched, right? And the velocity vector of the launching at the time of launch, the starting velocity is this vector right here. And we're going to be breaking that down into horizontal velocity and vertical velocity. And that's what this is. Whatever the velocity is here, that's what goes into there. It's the initial vertical velocity. Now we're going to be doing an actual example here, but know that gravity makes y have this complicated equation. But gravity only affects motion vertically, so the horizontal motion, the object will just keep going at this speed. So we're going to find that the equation for x is just a constant speed equation, right? Whatever the x value you start with, plus whatever this horizontal velocity is, so vx sub 0 times t, and it just keeps going at that speed without any extra stuff in the formula over here. So it's a simple linear equation. So here's our example with actual numbers. It says, suppose a ball is thrown at a speed of 73 feet per second at an angle of 64 degrees with respect to the ground. The ball is thrown from a height of 5.8 feet above the ground. Model the ball's position over time with a set of parametric equations. So note that unlike our remote-controlled car examples earlier, that was looking down and the car was running around on the ground, right? This example, it's a side view, and from the side, we're looking at a guy throwing a ball in the air. And let's sketch the situation. So we got the ground and the ball's being thrown. Pay attention to the starting position of the ball. It says it's thrown from a height of 5.8 feet above the ground. So that'll be the y value, right? But it doesn't say anything about the x value. So we can just start it at 0 for x. Here's the ball. It's being thrown by someone. Initial position is 0 for x, 5.8 for y, because it's 5.8 feet above the ground. And then it's being thrown at a speed of 73 feet at an angle of 64 degrees with respect to the ground. So its velocity is like this, perhaps. And then this angle with respect to the ground, I mean, that really means the angle with respect to the horizontal direction. Even though the ball's not on the ground, what that means is this angle of throwing, it's like 64 degrees above the horizontal direction. So we know this thing is going to travel in a parabolic trajectory like this. And then we want to model the position, like the x position equals some formula involving time, and also y equals some other formula involving time. And remember, we're given a velocity vector with a magnitude and a direction. And to write these formulas, we're going to need to break down the vector into its horizontal and vertical components so that we can use those horizontal and vertical components or speeds in the formula. And remember, how we do that is with that component form formula for vectors. So the magnitude 73 times cosine of the angle. Now this 64 degrees, can we use 64 degrees here? Is this 0 degrees? Yeah. So a cosine of 64 degrees, comma, magnitude is 73, sine of 64. So this will give us the components of the vector. And the horizontal velocity is around 32.0011, so almost 32 exactly. By the way, what is this? This is feet per second. And then the vertical velocity, around 65.6120, again, feet per second. So we've broken down the original velocity vector into horizontal and vertical velocity. Like we kind of said earlier, x is easy. It starts at 0. X position, the starting position is 0 plus, horizontally speaking, we can think of the horizontal and vertical motion independently. So with its horizontal movement, it just keeps going at this speed. So 0 is the starting position plus 32.0011 feet per second. So that's the equation for the x position. And then here again is the general formula for height over time, as in y position over time. So where does y start? 5.8. And then plus, we said this is the starting y position. We said this is the starting vertical velocity. So when it's being launched, what's the vertical velocity? We found that, right? 65.6120. 65.6120. And then it says times t here, don't forget the t, minus 1/2 times the acceleration of gravity. So remember this, when we're working with feet per second, is 32, times 1/2. So when we're doing projectile motion with feet in seconds, you're going to get minus 16 here. And then don't forget the t squared. And actually, we're done. These two equations, x in the horizontal direction, it's constant speed, it just keeps going this way. And then its height, the y position, it's parabolic, it's given by a quadratic equation. And again, we can use these equations to calculate things about the ball's position over time. Where is the position at this moment in time? How much time does it take for this thing to get to a certain position, etc. Now, one issue here, the equation for x is just a linear equation, so it's quite easy to deal with. By the way, we don't need 0 plus if we want to make the equation cleaner, because adding 0 does nothing. But the issue is the y equation is a quadratic equation. So when you're doing calculations with this, you might have to remember some things you learned about quadratic equations in your previous work. And I don't think it would be appropriate for me to go over all of that in this same video. Hopefully you've retained all that info about quadratic equations. And if I was to go over that stuff in detail, that would take like a whole nother video, right? But so far we've got the writing of the equations for the motion down here. And then we'll end this video with just a brief recap of things about quadratic equations in general. So, recap of quadratic equations or quadratic functions. So first off, for a quadratic function given by f of x equals all of that, ax squared plus bx plus c, the x position of the vertex is given by x equals negative b over 2a. So first off, remember the vertex of a quadratic function is like the topmost point, and this formula gives you the horizontal position of that point. Of course, parabolas can look like this as well, and so then the vertex would be like the bottommost point. Also remember that oftentimes when we're dealing with quadratic functions, you want to reorder everything so that the x squared term comes first, then the normal x term, and then the constant. And the a, b, c correspond to those terms. So a is whatever number is being multiplied with x squared, b is whatever number is being multiplied with the x, and then the constant is, the constant number being added at the end. And then also, for a quadratic equation, ax squared plus bx plus c equals 0, the solutions of the equation are given by the quadratic formula, all of this, right? And so remember, when you're solving a quadratic equation and you're using the quadratic formula, you have to get everything on one side. So like ax squared plus bx plus c on this side. And you have to make sure that one of the sides is 0. So before you apply the quadratic formula, you have to make sure to get everything from one side onto the other. And then combine like terms, reorder everything so that it's in this form on one side, and then nothing left over on the other side, 0. So those are some things about quadratic functions, quadratic equations that you should know. And that's it for this lesson. Good luck.